Hi students, I'm going to do a little video here on chapter 10 part C, and this material can be found in sections 10.8, 10.9 and well just 10.8 and 10.9 for now. 10.3 isn't going to be in this video. There are a lot of other videos I posted on Canvas that are from YouTube that relate to this topic. I want to go over something very specific in this video, and that is some heating curve calculations. You can watch the other videos for an overview, or I should say an overview details on the other topics that are in this PowerPoint. So we're on page 114 of the packet. So that's where we are now. And this is the same as what we have in the PowerPoint. I'm just using the packet so we can kind of write on these pages. And so down here, I'm not going to really talk about this. This is in one of the other videos. This is just the names of the different phase changes, okay, whether it's solid to gas, liquid to gas, etc. So make sure you know those. What we want to talk about in this video is something called the heating curve. That's what the main purpose of this video is. And a heating curve is a graph where you plot the temperature on the y-axis and the heat that you're adding on the x-axis. So it's temperature and heat. So remember, heat is a form of energy. So we're going to look at, as we add energy to a substance, what happens to its temperature over a wide range of energy being added. So you're adding heat energy, and we're looking at what happens to the temperature. Of course, in general, you add heat and the temperature goes up. We know that. But we want to look at the details of how this happens for different substances. Now, on these graphs, during a phase change, so a phase change is what was on that last slide where it says, you know, you're evaporating or you're freezing or you're melting, that kind of stuff. During those phase changes, adding heat causes no temperature change. So if you have some water in a pot and you put it on the stove and it's cold, and you start to heat it, we say you heat it up, right? Heating it up means increased temperature. So we're putting heat in, your stove is on, or you're in the lab and it's on a hot plate, and you're adding heat to it, and you have a thermometer and you in there and you watch the temperature goes up. Once it reaches the boiling point where it's undergoing, now it's undergoing a phase change, in that case from the liquid to the gas, the temperature stops increasing. It doesn't increase anymore. It sits there at approximately 100 degrees Celsius, depending on the pressure, as the water boils away. So during a phase change, there is no change in temperature. What's going on, we'll talk about that in a little bit, but you'll see a horizontal line in that case because the temperature is on the y-axis and it's not increasing. The length of these horizontal lines are related to what we call delta H of fusion and delta H of vaporization, or the enthalpy of fusion and enthalpy of vaporization. We define the enthalpy of vaporization. We stated that previously when we were talking about properties of liquids in the previous videos. And that the enthalpy, or the heat of vaporization, is the heat that it takes, the heat energy it's going to take to vaporize 1 mole of liquid. And you're doing a whole lab on that too, where you're looking at that, where you're finding that for water. So you have a liquid and it's going to a gas. And if you have 1 mole of that liquid, this is the amount of energy it takes in order to accomplish that. The delta H, or enthalpy of fusion, is similar. In that case, we have a solid going to a liquid, and we have 1 mole of it. So by similar, I mean it's the energy required to have this phase change occur. It's going to be a different number. And the delta H and the delta of fusion and vaporization are quantities that characteristics of a substance. We talked about how delta H of vaporization in the last video, how it varies with intermolecular force, because how much energy it takes to vaporize something, you're going to have to break a lot of intermolecular forces in order to do that. So more intermolecular force, higher delta H of vaporization. The same thing happens with delta H of fusion. It depends on intermolecular force. So the length of those lines are related to that. We'll show you what I mean by the length of the lines as we do this. So here's the heating curve. Slide this up a little bit. Okay, so there's a heating curve for water, okay? And there's one similar to this in your book. Slide this a little bit more. I'm going to zoom out just a little. Hold on one sec. Here's the tiny. See it better. There we go. Okay. So there's one in your book, figure 10.43. Okay. You want to look at that one. But this is the heating curve for water. So we're going to stare at it and kind of analyze it for a minute. As we said, we have temperature on the Y and we have heat on the X. And this is telling us that each division here is about 4 kilojoules, okay, on this particular graph. And we have this, we're calling it a curve. It's more like steps. What happens if you look at the points A, B, C, D, E, F, we're going to talk about all those points and what's going on. So down here, point A, this represents the starting point in this graph. And in this graph, we happen to start at negative 25 degrees Celsius. You don't have to start there. That's pretty random. You can start anywhere, but this is negative 25. Because this is for water, and this is going to be at 1 atmosphere. So we're just doing this in the open, 1 atmosphere pressure in a, in a lab or in a kitchen or something like that. So the pressure is this, approximately 1 atmosphere. So at negative 25, we're going to have ice, okay, because the freezing point of water is 0, and the melting point is 0. So we'll have ice. And so point A represents some ice. And then what happens is, as we go across to the right here, we're adding heat. So we're adding energy and we're warming up the ice. So what happens is the ice, to go from A to B, the ice is still ice, but now it's not as cold anymore. So now we've gone from negative 25 to 0 on the ice. Until we get to B, what we have is ice that is at 0, which is the melting point. And so then if you keep adding heat, which that's what's going across as we go across this line to C, we're adding heat because that's what the x-axis is. Now you're undergoing melting. So in the between B and C, you have a mixture of ice and liquid water, kind of a slushy kind of thing going on there where you have both. So ice, water, slushy mixture. And then when you get to C, you have gotten rid of all the ice and you still have water, but it's at 0 degrees. So it's cold water. So it's very, very, very cold water. So this represents the melting. So the length of this line, horizontal line here, comes from the delta H of fusion, because that's the energy, because the x-axis is energy, and this is the amount of energy it takes to melt that. If we were starting with 1 mole, and I should say that this is 1 atmosphere, and we are starting with 1 mole of water. So that ice would be 1 mole of it down here, about 18 grams, okay? Now we get to see we're at the liquid. Now if we keep adding energy by going to the right, what's going to happen is the water is going to start to get warmer, and we'll go through very cold water to room temperature water, the warmer water, eventually get to very hot water at D. Now D, it's very hot water, it's at the boiling point, okay? So what happens is when you get to that 100 degrees, if you keep adding heat, your water will start to boil. And it's going to boil, and it's good, but you have to keep adding this whole entire amount of energy. What's going on from here to here? Well, I'm adding more and more heat, and that is continuing to vaporize the water. So the length of the line from D to E represents, if I was to drop down to the x-axis here, all the way to DE, that's how much energy it would take to vaporize that 1 mole of water, to get it from the liquid to the gas. Now this line is much longer than this one. And that's because to go from a liquid to a gas, which is what we're doing here, you have to break every single intermolecular force present, because in the liquid, the molecules are touching and they have lots of intermolecular forces, and in the gas, they're far apart and they don't. So that energy is large because it's a lot of intermolecular forces to break. Furthermore, water has pretty strong intermolecular forces with our hydrogen bonds. Now down here, this line, the fusion line, what we call delta H of fusion, or the melting energy, that is not as strong, because even though we do have to break some intermolecular forces to go from ice to liquid, it's not as many as we have to break to go with the gas where they're completely gone. So that's why it's a longer line. Now, once we get to E, now we've reached the point where all the water's in the vapor phase. It's hot. We'd probably call that steam at this point. And you can then keep heating the steam. Okay, this is like be superheated steam, hot steam that's higher than 100 degrees. And we don't have to stop this at 125. That's just where this particular graph stopped, I should say. So this is a heating curve. You can also do a cooling curve. I could start at one point and then go back down and cool it. So that it could be that direction as well. Now, what we're going to do on this is we're going to do some calculations. We're going to figure out how much energy it takes to do some of these steps. If you notice, there's 1, 2, 3, 4, 5 possible line segments here. And each of those line segments is we're going to have to calculate a little bit differently. The problem that we're going to look at, we're going to have a lot of these line segments, but you don't have to have all of them. So let me just kind of go over the problem, and then we'll talk about different ways this could be asked. Okay, so calculations using the delta H of fusion and vaporization. The question says we want to calculate the enthalpy change, so that's the heat change, the total heat change for the process where we have 100 grams of water, and we're going to cool it now. So I said this can go in either direction, so I thought, well, let's try a cooling one. We have water. It's going to be a liquid because we're at 50 degrees Celsius, and we cool it to ice at -30. And then I have to give you a bunch of constants here. You need these constants to do the problem. We have what we call specific heats. Sometimes this is called specific heat capacity. We'll talk about what these are in a minute. Of the ice, the liquid water, and the steam are given. The delta H of fusion, that's that how much energy it takes to melt or freeze the ice, and the delta H of vaporization, and some hints here. Now, let's look at what we're going to do though. Back to the heating curve. So the problem says we have 100 grams, it's at 50 degrees Celsius. Okay, so that means we're not, in this problem, we're not doing the whole thing. We're starting here, 50 degrees Celsius, right there, there's 50. But we're gonna go down a little farther because it wants us to go down to -30. So maybe somewhere like down here. So let's look at how many segments of this we have. We're gonna have to, so what are we gonna have to do? The process says we're gonna have to cool the water down to 0. This way. Okay, we're gonna cool the water down to 0. Once it gets down to 0, we're going to have to go this way. So before we were melting, now we're freezing. So we're cooling the liquid, okay, in that step. Here we're going to be freezing, okay, that we're going to freeze it. And then down here, we're going to cool the ice down, which sounds strange to cool the ice down, but ice can be 0 degrees or -10 or -30. We got to get it to where they want us to be, which is at -30. Okay, so we have 1, 2, 3 steps. This is going to be a 3-step problem. These problems can be up to 5 steps long because I could have started from here and had this step and this step as well. We'll start with the 3-step, then I'll explain how to know for you to know how many steps there are. Okay. So we've got the 3 steps. Let's remind ourselves what we're going to, I'm just going to kind of write out the map. So we're going to go from liquid, we have 100 grams of the liquid, and it is at 50 degrees Celsius. The first thing we're going to have to do is cool that liquid down. So it'll still be liquid, but it's going to have to get to 0 degrees Celsius. It's going to have to go, we don't cool it and freeze it at the same time. We cool it and then we freeze it. Then we're going to have to freeze it. So that's going to turn into solid, also at 0 degrees Celsius. And then they want us to take that solid, which is the ice, and go to -30. So there's our 3 steps. Okay, we're going to call this step 1, 2, 3. Each of this is going to have heat involved in it. Now, because we're cooling it, we're taking the heat away from the system. This system is going to be losing energy. So the heat's going to be negative, meaning this is all exothermic. It's releasing its energy. The energy is leaving. It's going to the surroundings. An example of this is if I took 100 grams of water, that's, 100 grams is about 100 milliliters. So if you picture 100 milliliters in your head, it's not very much. You think about a 100 milliliter beaker in your locker, or a 50 milliliter beaker, think of that twice, so a little bit of water in there. And then we're going to have it at 50 degrees Celsius, which is pretty warm, okay? Warm water. And we have some warm water, and imagine putting that in the freezer. What's going to happen in that process in the freezer is the water is going to cool off. So at first, before it freezes. So where did that energy go? If it was warm water and then it's very, very, very cold water. Well, the energy left the water and it went into the surroundings of the freezer. So the freezer had absorbed that heat. So that makes this an exothermic process. If our system is the water's losing the energy. Then once it gets down to very cold water, it's going to freeze and become ice. And we have to take more energy out of it now because the water molecules here in the liquid, they're moving around. We have to cool them till they're moving around much more slowly and they freeze. And so that's going to take energy to remove that energy. And then we have to remove more energy to get the ice colder. So 3 steps. Okay. Now, what are these numbers here? Well, the specific heats, or sometimes called the specific heat capacities, if you notice the units here, they're in joules per gram degrees Celsius. And what this tells us is how much energy it takes for these 3 phases, ice, liquid, water, and steam. Let's look at the liquid water, for about 4.18 joules per gram degrees Celsius. That tells me, let's say if I was heating up the water, it's liquid, how many joules it takes to raise 1 gram of water 1 degree Celsius in temperature. So if I have 1 little gram of water, that's 1 milliliter of water, okay? If I have that 1 little bit of water and I have it at, let's say, 25 degrees. If I wanted to get up 1 degree to 26 degrees, I'm gonna have to put 4.18 joules in. It's the same amount of energy if I'm going in reverse. If I have it at 26 and I wanna go down to 25, that liquid water, I'm gonna have to take out 4.18 joules for every gram to go down a degree. So that's what the specific heat is, or the specific heat capacity. It's how much energy you have to put in or take out to change the temperature by 1 degree for every gram. It's different if you have ice, liquid water, or steam. Now, in the problem we're doing right now, we don't have any steam. We're not going to steam. We're not starting with steam. We're not going to need this number. I put it in here to be complete, so if you needed it for a homework problem or something else. So we're going to need these 2. Then we have 2 numbers down here, the fusion number, delta H of fusion. This is how much heat has to be put in to melt ice. And this is given as about 6 kilojoules per mole. So in this case, we're not doing it per gram here, we're doing it per mole. So it tells us we're gonna need about 6 kilojoules to melt 1 mole of ice, which is about 18 grams. It also tells us we're going to have to remove 6 kilojoules of energy in order to freeze it, because melting and freezing is just reverse processes, takes the same amount of energy in reverse. This is the delta H of vaporization. You studied this in lab, or you will study this in lab shortly. And this tells us it takes about 40 kilojoules per mole to vaporize the water, or if we're condensing it, going from gas to liquid, we'd have to remove 40 kilojoules per mole. We're not going to use this number in the problem we're doing at the moment because I'm not doing anything with a gas phase. I'll show you where that would come in a minute. Let's look at the one we have. So what kind of steps do we have? We have the first step is the liquid that is warming. We're going to need this number for it, the specific heat. So the 2 equations is that when you are doing a temperature change step, we're not doing a phase change, we're just changing the temperature. The formula is the heat that is involved is going to be the mass times the specific heat times the change in temperature. And delta T is the final minus the initial temperature. That's where the sign is going to come from, negative or positive, because the mass is always positive and S is always positive. So what's going to give us the sign on the Q, or the heat, is going to be the delta T. So that's for a temperature change step. Now, the other kind of step we could have is a phase change. For a phase change step, which you could call change of phase, the Q will be equal to, here's the tricky part, positive or negative delta H, and this could be fusion or vaporization, depending on what step you're doing, times moles. Okay, so what's this about? Well, this formula works whether you're doing the fusion. So fusion is when you are going solid to liquid or liquid to solid. So freezing or melting, you use this. Okay, so fusion is for freezing or melting. Okay, and the vaporization, that's this guy. Vaporization, the delta H of vaporization would be for vaporizing or condensing. Same number depending on which direction you're going to. Okay, so we're going to keep that in mind. Let's go back up here. So let's look at our steps here. We've got 3 steps. What kind are they? Well, we got this one. We got a liquid, so we're not changing the state on this arrow, liquid to liquid, but we're changing the temperature. So this is a change in temperature type step, this kind of Q here. This one, the temperature is not changing, but we're going from liquid to solid. So 2 is going to be a phase change step. 3, we are not changing the phase, solid to solid, but we are changing the temperature. So change in temperature. So now we know what our 3 steps are. We're going to have 3 Qs on this problem. Q is heat. So 3 heat changes for 3 different steps. Okay, so the first one, Q1. Remember we said it was Q1 was a temperature change, so we're going to use this formula. I'm going to copy it down. Mass, specific heat, change in temperature. Okay. Mass in the problem, 100 grams. Specific heat, well, we're in the liquid stage, so I'm going to move this out here. Our specific heat of our liquid is this one. So ice, liquid, and steam or gas. Ice, liquid, steam, or gas. So we have this, the liquid, 4.18 units of joules, grams, degrees Celsius. Change in temperature. And we said earlier that is final minus initial. In this step, it's the change in, this is what one of the biggest mistakes students make. It's always sad, they get the whole problem right, and they mess up this one step. This is the change in temperature for this step. Okay, the change in temperature for step 1. So for step 1, our final is 0, our initial is 50. Don't worry about the negative 30, that's another step. But over here, for this step, it's 0 is the final, because we started at 50 and we went to 0. So final minus initial, 0 minus 50, and that was, 1 sec, 0.0. Okay, so mathematically, what's going to happen with the units, even before the math, grams, grams, Celsius, Celsius. And then if you do that, you're going to get, I think I have it written down, This is going to be negative 50. And so my answer is going to be negative 2.09 times 10 to the 4th joules. Okay, so that's my Q1. All right. I didn't say this in the problem, but it's going to become much more convenient to do this in kilojoules because these are going to be big numbers. And that's usually how the answer is given. 1,000 joules in 1 kilojoule. So I'm going to divide this by 1,000. That's going to give me a 10 to the 1, negative 20.9 kilojoules. Okay, for step 1. Okay, step 2. Step 2, whoop, up here, that's a phase change. Step 2 is a phase change. There is no change in temperature. There's no delta T. So we're going to do the phase change one. And this phase change is the liquid to the solid. So we're going to use this equation here. So since it's liquid to solid, we don't have to worry about vaporization. We're going to use the delta H of fusion. So let's copy that equation down. Q2 plus or minus delta H of fusion times the moles. Now, what's this plus or minus business? Well, the energy can be going up or down. The delta H of fusion just tells us how much energy it takes to freeze or melt. You got to decide whether the energy is coming or going. A big indication is if you have this step, if this is negative, then this one's going to be negative as well. Or if you really want to think about it, if it's only one step, you got to kind of think about it. Or if that's your first step. And over here, if you think about it, we're going from a liquid to a solid. So the system, which is the water, is losing energy. If it's going to freeze, it's going to lose energy. And that's why it's negative. Okay? So you could think of it either way. Either, hey, this one was negative, so I'm going to keep going in that direction. Or the better ways to think of what's happening is I'm losing energy. So this is going to be negative. Now my delta H of fusion was given in the problem over here. Got to be given. These are different for every substance. These are all for water. Every substance has its own set of these. So it's 6.02 kilojoules per mole. That's why we need moles here. Up here we use grams because this is given in units of grams. Sometimes this is given in units of moles. I've also seen this is almost always in moles. This is sometimes these specific heats are usually given in grams, but once in a while moles. But for you, I'll give you this one in grams and this one in moles. Now, how many moles do we have? Well, we have 100 grams of water. So we got to do a little conversion over here. 100 grams times 18.016 grams is 1 mole. Okay, so at that point, I'll be at moles. That'll cancel. Okay, and let me see where I am here. That'll give me negative 33.4 kilojoules. So this one's already in kilojoules. Over here, the answer came out in joules because this was in joules. So I had to do the 1,000. So to get to kilojoules. This one has kilojoules on the constant already. So the answer comes out in kilojoules. So that's the energy that we have. The freezer has to pull out of the water in step 2 to get that very cold water now to actually freeze to solid ice. So at this step, we'd have ice that's solid, not super solid, not really hard because it's just right at 0. It's at that melting point. You know, it's kind of ice that would be easily melted really quickly, but it definitely is solid ice. So step 3. Okay, let's go back and look. That is our, now we have our frozen ice at 0. We want to get it to be very frozen, very cold at negative 30. So this is a change in temperature step. So we're going to use this equation again. Q equals ms delta T. Mass is still 100 grams. The specific heat, have to use a different one because now we're at ice. And the ice has a specific heat of 2.09. So ice, liquid, gas. So 2.09. Back over here. Oops, this is supposed to be joules. I wrote grams. Joules per gram degree Celsius. Okay, sorry about that. It's a funny joules there. And then the change in temperature. And again, this is the change in temperature for this step. And this step, the final temperature is -30. The initial is 0. So it's only for this step, the delta T is for. -30 and 0. Okay, bring that up so you can see it better. Okay, so we do that. The Celsius will cancel, the grams will cancel, and I'll be at joules. And that is 6.27 times 10 to the third joules. Got to divide by 1,000 to convert to kilojoules like I did in the previous step. I'm sorry, and this is a negative because this is negative here. -30 minus 0 is negative. So negative, you'll have a negative number here. This is to convert to kilojoules, -6.27 kilojoules. So that divide by 1,000, that's this step here. I just ran out of room to write it all down. So now we have these three, okay? And what we're gonna have to do to get the final answer is to add them up because we want the energy change for the whole process. So Q1 plus Q2 plus Q3 equals Q total. And that is my -20.9 plus -33.4 plus -6.27 kilojoules. And that comes out to -60.6 kilojoules. So that tells us that if we have 100 grams of liquid water, that's warm, pretty hot, 50 degrees Celsius, pretty warm there, and we are going to freeze it all the way to ice at -30, we're going to have to remove -60, we're going to remove 60.6 kilojoules, or it's going to have to lose 60.6 kilojoules of heat in order for that to happen. So, excuse me. So what else, how else can this be asked? This is, one problem. Well, if you look at this, if we go back to our heating curve, which is here, I asked you a 3-step problem, 1, 2, 3. And I was going in the negative direction. I could ask you the same problem in the positive direction. You'd get the same answer, but it would be positive. I could ask you a 5-step problem, 1, 2, 3, 4, 5. In order to get this step, you'd have to use the delta H of fusion. Okay. In order to do this step, you'd have to use the specific heat for the steam or the gas. Okay. So that would be so this would be a delta T step. This would be a phase change step, okay? So the same equations, but you'd have to use different constants. You could do anything from a 1-step to a 5-step. Sometimes students practice these, and then I ask what I think is a simpler problem. I give them a 1-step problem, and they get all confused. The typical thing that happens on these problems where students make mistakes is they try to combine the steps. So they don't analyze their steps. And instead they go from here, count this all as 1 step. The other one is the one I mentioned before, where they see the final and initial temperature and they don't realize that it's per step. Okay, so it's the temperature change for that step. So they look at the 50 and the -30 and they look at it's per step. So 50 to 100 for this step, 100 to -30 for this step. So there's more of these to try in the homework. There's another one in the practice questions. So make sure you try those and you can do those. There'll be for sure be one of those on the next exam, some type of calculation of energy off of a heating curve. Okay, I'm not going to go into lots of detail about the rest of this PowerPoint because I have a lot of other videos posted on these topics, and this is more about understanding than calculation. I do want to point this out as long as we're here because we just did one graph and now this is going to switch to a different graph. So there's other videos about these phase diagrams that I want to mention a little bit before I let you go. So this is the second type of graph we're looking at in this set of notes. Why are we doing this? Why are we doing two of them? Well, they're showing us different things. And in this one, this is pressure of the air above or whatever, the external pressure on a substance and the temperature that we're graphing. And what happens is, this is called a phase diagram. And what it tells us is if we look at the pressure and the temperature that this substance is at, is it a solid, is it a liquid, or is it a gas under those conditions? So we're used to thinking of things as, well, water is a liquid and carbon dioxide is a gas and iron metal is a solid. But all of those things can be different phases. You can melt solid iron to make it a liquid. You can take liquid water and turn it into a gas, or you can turn it into a solid. Carbon dioxide can also be turned in from a gas to a solid. So what phase it's in depends on the pressure and the temperature, but it also depends on intramolecular forces. So all of those substances can undergo these changes from solid to liquid to gas, but what temperature, what pressure it happens at is dependent on their intramolecular forces. Turns out though, if you make a graph of pressure and temperature for any substance and look at its phases, you're going to get one that's shaped pretty similar, like this. Kind of like a weird Y shape, okay? There's going to be some little differences that some of the videos will talk about, but pretty much like that. And what happens is what happens is this line here. This line represents the transition. If you were right on this line, so if my pressure and temperature get me right there for this substance, this is water. So if I found the pressure and I found the temperature and I graphed it right there, that means that substance, in this case water, at that point would be on the line between a solid and a gas. This is a solid, liquid, gas. It would be sublimating. If you graphed the pressure and the temperature and you found it's over here, you'd say, oh, that's a gas, because this is it's all gas. Over here, liquid, over here, solid. So these lines represent, if it lands on one of those lines, that's where a phase change is going on. So this is the phase change, solid to liquid phase change. So if you have, think about this way, let's say we have a pressure. Let's say this is our pressure right here. Maybe that's 2 atmospheres. And I start out at this temperature. Maybe that is, negative 20 degrees. And so I start right here. Okay, that tells me I have a solid. If I stay on this, what happens if I increase the temperature? Remember, temperature's here, so increase would be going that way. So if I hold the pressure constant, just let it sit out in the atmosphere, and I heat it up, what eventually is going to happen is I'm going to reach a point where it gets to this line. When it gets to this line, it's going from the solid to the liquid, so it's going to start to melt. When it melts, it's going to be over here. If I keep increasing the temperature, eventually I get to a point, I keep going, where I get to, and I vaporize it to the gas phase over here. Down here, if I start here with the solid, if I'm at a lower pressure and I start to heat it up, I eventually hit this line, and then I cross into the gas so you can go from the solid to the gas without crossing into the liquid. That's called sublimating. Where this all happens, where the pressure and temperature, and the triple point means I got all of them happening at once. Talk about that in one of the other videos. The pressure and temperature that all this happens at depends on the substance, and it depends on its intermolecular forces. So all substances have this kind of a phase diagram. Some phase diagrams get more complicated because there's like 3 different types of crystals in the solids, so you might get branches, but don't worry about those. So there's going to be more videos on phase diagrams. I just wanted to point out what it was and what it's telling us a little bit better. So I'm going to let the other videos tell the story on that. There's no more calculations on that. It's all just definitions and things. So we're going to stop here on this video and talk to you next time. Thanks.